Everyone, thanks a lot for being here. Today today we are going to talk a little bit about full text search. This is a project we have been developing at Couchbase. So first of all, my name is Denis. I have been working with. 10 years ago, I had a startup related to search engine optimization, and since then I have been working a lot with Solar and with search in general, and that's basically where my experience with search comes from. I'm also a developer at Couchbase. So Couchbase is a NoSQL database, very similar to Mongo, but designed to scale a lot. So an average client with Couchbase would have like something around 15 nodes at least. But in general, we have clients with like, in a single cluster, more than 100 nodes. So it's a very, it's a database really designed to more critical scenarios. And if you guess why we are talking about full text search, turns out that for us, we have, like LinkedIn, PayPal, eBay, all those folks use Couchbase, and they also want to do full text search on this database. But when you have like a single cluster with 100 nodes, you might guess that's pretty hard to. Oh, sorry. You might guess that's pretty hard to make some full text search. It's hard to push data to Elasticsearch or push data to Solar. So we decided to create. There is also some issues with Lucene, which is basically the framework that most of those applications use. So Lucene is Java. We have a lot of issues with JVM. So we decided to create something from scratch, which is called Blivy. So Blivy is very similar to Lucene, but written in Go, and designed to perform well at scale. Okay. So yes, first of all, this talk is mostly about live coding, because yeah, we YOLO, right? You just live once, and let's live coding in front of 400 people. Okay, let's start. So search in general, one thing about search is it's not about matching text. So this is one common misconception. Search is something very sales-oriented. Yeah, so Netflix is, when you search something to Netflix, they are trying to convince you to watch a movie. Even if they don't have the movie there, they will recommend some other movies. Google, they are trying to answer a question and showing ads, and on Amazon, they will try to show you products that you want to buy, even though your text is not the exact match of what you're looking for. They will try to give you the best product possible. When you are building some search application, one of the key things is to understand how your users search. So, for instance, this is an old research related to Google. This is basically how users search on Google. And if you see, nearly 6% of the users use up to 3 keywords. And that's basically why you have to make a decent recommendation to them. Of course, when you're building a search, it's very, very important for you to save the user query, save the results you show, and save which results the user clicked. Because then, later on, you can implement the text and try to improve your search based on what the users are choosing. Some quick concepts here. So TF-ADF it's a very famous algorithm. So basically, it means that words in a text documents with words will rank higher. Edit distance is how many operations it take to transform one word to another. So, for instance, if I want to transform star to start, it only takes one operation because I just have to add one letter. And pivotal length normalization means, okay, a text matched in a tweet, for instance, in a small text, will rank higher than a text matched in a 50-page long document. So that's basically some key concepts here. Okay, so let's start coding here. So first of all, I have a very simple application here. So what the application do here is it gets a word from some phrase from the front end, and basically execute this in a search algorithm in our indexer. So just to show you something here. So this is when you install Couchbase. This is the web console, and we have this search here. We have a very simple index, which basically index the whole database. And what's running here is actually believe. This is what we run internally, and this is again 100% open source, and that's what we run here internally. My database have nearly 200, more than 240,000 documents. And yeah, and what we are doing here is just, okay, let's pick the word that we have and match to the text and search in our database. So I built a very simple application here called Couchflix. And well, let's start to search for something here. So let's search for Star Trek. Okay, not bad, right? We are just picking the word here and searching our database. What about Star Wars? Yeah, we have a lot of movies here not related to Star Wars. Okay, let's try a typo here. So Star Wars. And, well, terrible. Even though we understand that, okay, I know what everyone can understand what you're looking for, but the results here are terrible. One of the reasons here is because by default, when you're using the same concepts like here, you can apply to Elasticsearch, to Solr, or to whatever you can think of. Basically, all the search engine frameworks, they behave the same. So one of the reasons here is because we are searching in all fields of the document, and this generates a lot of noise. So in order to improve our search, let's try to create here search 2, and then we can change here for search 2. We create disjunction query. So disjunction query is very similar to an OR operation, and let's search just for the title. So I can search for get disjunction query, disjunction, and then I can pass the word and then title. Right? And then we simply search here, we pass the title, and we delete this. Okay, let's recompile. Let's duplicate our tab here, and let's search for Star Wars again. Well, it doesn't look like we have any improvements, right? So maybe we could try to add more fields then. So let's create search tree here, and search for search tree here. And now, instead of just searching for the title, we will also search for overview. And let's also search for original title. Okay, and now to join all those queries, I have to create another disjunction query, which is, again, just an OR operation in SQL, very similar to SQL. So FTS equals to search query, disjuncts, and then I use title, overview, and original title. Okay, great. Now we remove here, FTS, recompile, and let's duplicate here. run. Okay, and now let's try again. Star Wars. Still not bad. I mean, still terrible. What's happening here? A lot of developers, first thing they do is to boost fields, and this is by far not the right approach. What's happening here is basically we are matching those two texts separately. So if I have a movie which has star, 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 and a movie which has in the title Star Wars, the movie that has star, star, star in the title will rank higher because it will be more relevant here. So we have to think about how do I index my data. So one of the there's different types of indexing. One of the most famous one is called shingle. So a shingle, instead of indexing words separately, it will create a combination of any number of words. In this case, if I have a combination of 2 words, it will generate keys with the values of Star Wars, Wars Daisy, and Daisy Headley. So we can actually create very relevant keys for what we are looking for. I already have the index created here because it takes a while for an index to create in a database of this size. So basically, I have movie shingle. I have all the fields I want to index here. And if you come to, you see that I'm using a title analyzer. And then down here on title analyzer, I basically convert the text to lower. I remove stop words, so and, I, or all those kind of words we remove. And then we have shingle simple, and shingle simple, basically I broke the text in combination of 2 words. Of course, we have many other analyzers here. So for instance, in Ukrainian, I think if you say ya тебя люблю or я люблю тебя, it kind of have the same meaning. So you can create something like anagrams. So it creates multiple combinations of the phrase, and they all will mean the same thing. But for this case, yeah, we don't need shingles are good enough. So let's go back to our code here and create search for. And with search for, what we can do is to basically, let's simply just change the index name. So same thing we have been doing in the past, but with a different index using shingles now. Okay, let's recompile. Oops. We can come back here now. Yeah, this was our last. Let's duplicate again, and then search for Star Wars. Yeah, that was the issue there. Okay, so we are getting there, but Plastic Galaxy or this Star Wars documentary here, they are not the most popular Star Wars movies. So we really want to show the best Star Wars movies ever, or at least the ones that the user really wants to watch. So one of the things we can do is to, we also have steaming, so it's also another type of indexing you can use. So in the steaming basically converts the word to the root, converts the word to the root. So fishing, fish, fished, fisher, they all are converted to fish. So you can remove a lot of the conjugation of the verb. So for instance, yadoma will be converted to yadom, or something like that. So yeah, now we can also think about ranking factors, right? Because now we want to recommend the best movie possible for the user. So when you think about ranking factors, you have to think about what's relevant for you, what makes the movie great. So for Google, it's important the title, the URL, the content, the amount of links you have to your document. On Amazon, description, specification, photos, customer satisfaction. So those are all ranking factors. So some of the types of ranking factors you can use, you have general data about the item. You can also use signals. So how often a user choose this item or this result. And you also have like personalization. So for instance, if I prefer comedy over science fiction, you probably might boost an application with a result with comedy. Yeah, this is just an example of some research on how Google distribute the ranking factors for local search. So basically, one of the main things here is link signal. So link building is something very important for Google for ranking. And yeah, and also when we talk about ranking factors, usually you have to start guessing what are your ranking factors. So you say, okay, title will worth 30% and description 15%, actors 20, and so on. We also want to, one common thing is also boost by release year, right? So release year is something very important. If the movie is from 2019, well, it's a very recent movie. If the movie is from 2018, okay, yeah, it's not so old. But if the movie is from 2004 or 2000, I basically don't care that much. So I can simply boost by the year. I have some different relationship here, right? If the movie is from 2019, I really care a lot, and I want to show this movie first. But kind of doesn't make a difference if the movie is from 2000 or 2004. You can do this with Gaussian functions, or Gaussian decay functions. So basically, a little bit of math. So you just apply some math to your ranking function, and then you can have this kind of behavior. This is, for instance, how Hacker News work. So I don't know if you guys are familiar with Hacker News, but no matter how many upvotes a news has, in pretty much a few hours or one day, it will be out of the front. The first page. In Believe, although we can do this in Couchbase with user-defined functions, we don't have this feature yet in Believe, but we can emulate with range queries. So I can say, okay, if a movie is up to 4 years old, yeah, boost for 25%. If a movie is from 5 to 8 years old, boost in 5%. If the movie is between 9 and 18 years old, penalize in 10%. So here I'm decreasing the score, and so on. So let's do this here. Let's implement now search 5. Search 5. And create a function here. So one of the things I will do is basically let's boost title for 40%. Overview usually have a lot of words, but so maybe it doesn't work to boost at all. And original title 10%. And then let's create a conjunction query, which is an AND, basically. And this conjunction query, I will join this OR here with my boosting release here. Okay, yeah, search query, conjuncts. And here. Okay, let's try to run this code and see if we have some improvements. back here. Duplicate. Star Wars. And yeah, we are getting there. So for instance, Force Awakens, now it's closer. So yeah, we got some improvements. Of course, here I have all the scores, so you can see why one is ranked higher than other. And we also have here, for instance, a lot of all the data we have to the movie, so we can pretty much use all this data here. So yeah, we are getting there, I think. Let's try now to see what else can we add, and let's add more attributes. What about ratings? So yeah, ratings makes a lot of sense to add ratings, right? There is some issues with ratings. So one of them is a 3-star movies for me could be a 5-star movies for you. So how do we have to normalize the data when you are dealing with ratings. We are not doing this here, but we are doing another thing, which is, okay, what's more important? A movie with 20 votes and 5 stars, or a movie with 3,500 votes and 3.8 stars? So you can just use votes directly. You have to compile. One of the things you can use is come up with some algorithm or some function to apply some confidence. So how much you are confident in this value. This is a very simple one, but works pretty well. So for instance, if we use this confidence interval, we have like Robot Chicken has 6.8 votes, an average of 6.9 stars, and the confidence is 1.7. While Star Wars has more than 6,000 votes, 8.1 average, and more than 7 in confidence. So you can use this confidence function to combine number of votes and stars to have a meaningful number. Yeah, and of course, sometimes, I don't know, you have some sales, some discounts, and you can also just say, okay, I don't care if the user search for this term, show this result as the first one, and then we can sell more of this product. So we could add a lot of attributes here. So let's say, for instance, we can come here now and say, search 6. What's going on here? Search 6. Then we come here, search 6. Now we have boost release here. So let's add. I already have the code here to boost by rating. This is exactly the formula I had. I also have promoted. So the promoted is a Boolean flag, and if the movie is promoted, I boost the result a lot. We also have popularity. What else? And boost. What have we have? Yeah. Boost popularity, release, runtime. Yeah. How much time the movie was in the theaters? So now, yeah, that should be good enough. Let's run our application again. We're good in time. Okay, our application is running. So here, let's duplicate. And, well, here's our result. And let's search for Star Wars. Yeah, so now I think we have a pretty decent result here. We have the original Star Wars movie. We have the Force Awakens, Rogue One, and then we have a comedy, and yeah, pretty much okay. Yeah, it seems to be a good search. What else can we do to improve our search here? So one of the things we can do is to add facets. So facets is this part here. in the side when you need to search for, when you search for something like notebooks, it will give you a lot of things on how you can filter your search. So, okay, let's copy our search 6 here. Create search 7. 7. And now what we can do is to first, let's receive here our map of facets. Okay, facets. And if the facet yeah. Now if facets is not empty, okay, then we could use your conjunction query. Oops, let's move this a little bit. Conjunction query and add facet filters, and here we can do something like our conjunction query and facets. So here we are basically filtering the facets we want, and here I say, okay, query.add facet, and I can say genres. I want to filter by genres, and then search facet term, genres.name, and here I want 10. Yep. So genres.name, this is coming from my index here. So my index actually has genres.name. So this is what I'm referring to. Do I have any other? Yeah, should be okay. Oops. Yeah. Here I have to pass the facets. And let's compile. And hopefully now if we duplicate the content, I can now search for a Star War. And I can filter here now by comedy, by drama. So basically, this is some of the things you can do with facets. Let's go back to my slides. So one of the things you can also do is, of course, you have to understand what the user is searching. So let's say he's searching for actors, right? Our search is heavily biased on titles. So if I recognize that the user is searching for an actor, I have to rethink about my boosting parameters. Even Google, for instance, if I search for table, yeah, internet is slow here, but Google doesn't know, are you talking about actual table? Are you talking about a CSS table? He doesn't really understand. So he always tries to parse your query and understand what you're trying to accomplish. This method has kind of a B refactoring, but let's just go through it. Yeah, now search 8. And let's add search 8 here. Let me uncomment this. So in this method here, what I'm doing is I already have a database of actors. So I parse the query and try to understand if there is an actor name there. And if there is an actor name, I basically change the boosting field. I change the value here of the boost field. So yeah, and same thing for genres. So if I identify that I have a genre in the search term, I basically change the boosting field. So instead of boosting title for 40%, I will boost title for just 10%. Because now what's important is the actor's name. So let's try to recompile our code. Here. And here again. Hopefully, let's duplicate. And OK, let's try to search for Eddie Murphy here. Yeah, in the internet is not working pretty well. Let's try to change the network here. Forget it. Yep. So then we have some issues with internet. Nope. Let's change here to this one. So one of the problems let's go back to my slide then. So one of the problems with entity extraction, which is like recognizing there is a category or an actor, that is something very difficult to do. And you don't have to do it by yourself. So Solar, for instance, has a Solar text tagger. Elasticsearch has a lot of other plugins for that also. You can always use some cognitive service to understand what the query is about. Of course, you have to do this before the query. So in a job to try to find some entities, because on the search itself you have to be as fast as possible. And of course, TF-ADEF have both TF-ADEF and pivotal lane normalization have a lot of pitfalls. One of them, let's see if the internet is back here. Eddie Murphy. Yeah, not yet. Conference. So one of them is, in this case here, I have movies. Let's inspect. I have movies with, this movie here has maybe just 2 persons in the cast, and there are other movies that have like 50 actors. So this also kind of screw up with relevancy, because a movie with just 2 actors, and you have exactly the name of the actor you're searching for here, will rank higher than a movie that has 50 actors in it. But in this case here, it doesn't matter how many actors I have in a movie. I just want to match the user and boost for the other ranking factors. So what I have to do is basically normalize your array of actors. In this case here, I can simply come back and say, OK, instead of using actors, the array of actors, I have a adjusted array of actors. So all the array of actors have the same size in all movies. So this way I can compensate to these issues with TF-ADEF. And then I can run my code again. Oops. Yeah, I'm running. OK, let's duplicate. And let's say search for Bruce Willis. So yeah, internet is not helping me here. But yeah, we do have some like Bruce Willis movies here. One of the things we can do with this search is, because we are extracting entities, we can also do something like Bruce Willis comedy, for instance, and we still have like a lot of movies related to Bruce Willis. You will still get the moves here. While if you go, let's go to Netflix here and try to search for Bruce Willis. So yeah, so for instance, in Netflix, if you search for Bruce Willis comedy, it won't bring the same results as we have here. So even though we spend like just 40 minutes implementing a search, it will be, in some sense, as good as Netflix search then. Let me go back to TF-ADEF. So Of course, when you're implementing tests, you don't. When you're coding a search, you don't implement like I did here, because you have to use some evaluation. You can simply run. You can simply run, let's say, JUnit tests. You have to use some method called Cranfield evaluation method, which basically shows how close you are from the ideal result. And of course, you have to use precision and recall. So every time you change a parameter, you have to say, okay, what's my precision and what's my recall for this change here? You never have to change like many parameters like I did at once. Be careful with black hat. So for instance, if you have like star, 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 star many times in my description, this will probably rank higher. So that's why, for instance, on Amazon, whenever you you announce a new product, they review your announcement to be sure that you are not trying to rank higher than you should. So you basically, because of course, if you rank higher on Amazon, for instance, that usually means that you will sell more products. And for the reading, of course, Believe Search, something you guys might check it out because it performs really well at scale. Relevant Search is a really good book. Dumbing Text, it's also a basic recommendation. We also have this course on Coursera called Text and Retrieval for Search Engines, a basic course for you if you want to understand a little bit of search. And the cool thing about this is something that you can actually use tomorrow whenever you are implementing a very basic search in your application. What else I have here? Do I have internet back? No. Where's Willis? Wait, this. No, I don't have internet here, but yep. And just finish. And yeah, thank you very much. I hope you guys enjoyed.
We have one question, and I think the whole audience will ask the author of this question to be concise and brief, because, well, a lot of us are starving from hunger, and the lunchtime is, well, you see. Mm-hmm.
Hello, my name is Max, and your example with searching TVC is very good, and I have a question. Is there any examples of searching with dynamic algorithms?
Sorry? Searching?
Dynamic algorithms. Is there any examples?
Like which kind of dynamic algorithm you
for example, if I in a good mood or some, can this algorithm track my mood?
Yeah, I mean, there is many types of algorithms out there. Like if you use Elasticsearch or Solr, you already have a lot of plugins that will parse your query and understand the entities and do probabilistic matching. For instance, let's say you search for senior Java developer. Those three words are usually in a probabilistic parser, for instance, it will understand that, yeah, these words are usually matched together. So I will, instead of separate like shingles, when I would separate something like senior Java and Java developer, it will match all those words together. So search is a very wild field. So there's pretty much a lot of algorithms there. I do recommend you to search for plugins first. And there's going through those books, and you can, from there, find out a lot of search algorithms.
Thank you.
Thank you.
Well, any more questions? If no, then thank you once again.
Thank you.